Today we have the pleasure to host Jonathan Vacher. Jonathan was trained in mathematics at the ENS Cachan, was ENS Cachan at the time, now that's ENS Paris-Saclay, which is just there. I can see it by my window. Then he did a PhD at the crossroad between math and neuroscience under the joint supervision of Gabriel Perret, was a mathematician in the ENS Rudulm, and Cyril Monnier, who is a neuroscientist working at the CNRS campus in Gif-sur-Yvette, and was now moved to Neuropsy, that is also just next door. After his PhD, Jonathan did a postdoc, several years of postdoc with Ruben Cohen-Cagli in New York, and also with Pascal Mamassian in Paris at the ENS Rudulm. And I think that the work is going to present today is mostly derived from this postdoc research. So Jonathan is interested in vision, and in particular applying probabilistic segmentation to understand vision, and also the modeling of textures. So thank you, Jonathan, and the floor is yours.
Yeah, thanks a lot. So yes, so today, thanks everyone for being here. I'm really happy to be able to present here. Yeah, so I will mostly talk about my work on synthetic texture here. So I will start. So yes, so during my PhD, I started to work in neurophysiology, as Florence said. So in the lab of Yves Frignac and Cyril Monnier, where they were doing recordings in the cat. And my goal here was to develop a set of some computation tool to generate stimulation and stimuli, like so visual texture and dynamic textures. And I also started to work in collaboration with people in Marseille, Laurent Périnet, Guillaume Masson, where I started to also propose the use of this stimuli to study perception. So I was trained both in psychophysics and I have some knowledge about neurophysiologic method and data analysis in this field. And the goal here is always to understand the relation between the stimulus and the responses of a user, or whether it is recordings. And so the goal, if you want to understand the relation between the two, you have to understand the stimulus. So this is what I started to work on, and to propose and to develop some mathematical model that would be further used to model the relation with the response. So visual stimuli that are used to be used in neuroscience and vision studies are mostly. So we started in the industry by using artificial stimuli, so like dots, gratings, or simply bars, and then we moved also toward using noise, and more recently, like the last 20-30 years, people start to use natural stimuli. So you see that you go from simple things to random things and to highly complex images. So there is a need of modeling everything. Here, if we understand, we define the pixel value. Okay, this is well understood. Here we can define a probability distribution, but here it's getting more complex. And so there is room in between all of these stimuli. So in computer vision, one approach is to distinguish natural images from textures and from contours. So in an image, you find textures that are delimited by contours. So I spent some time working on the segmentation and contours during my postdoc, but here I will focus on what I did on my work on texture during my PhD and also during the postdoc. So I started asking, well, after starting, like, what is our approach on the brain? And I think this is a dominant approach. So we are all like using materialism and physicalism to understand the brain. And this recently led to functionalism, which can be understood with a small syllogism. So the brain is an organ has a function, and therefore the brain has a function. And so our goal is to understand the brain function, what it is. And so during the 50s with information theory, evolution, and so with Shannon and also Turing, well, we understood the brain as an information processing system. So you receive information through your sense, and you treat them to behave. And so this is related to different stage question, how to represent the information. So how the brain represents information. And honestly, this is really an open question. There are many ways. And also a key question is how to handle uncertainty. So behaving in an environment where we're not able to collect all the information available, just a part of it. And so it's always there's always a lack of information. So how do you handle that? And so all the mathematical tools, of course, are from information theory, signal processing, probability, statistics. So this is where I'm situated in the field. And so this is the few equations that we will be using during this presentation. So the hypothesis on how the brain processes information is that perceptions are internal representation R of the external world S. So R is an internal variable and S is a physical variable outside the brain. And we say that these measurements are noisy, so they are corrupted by noise. So you go through function phi, and then you are corrupted by noise n. And from these measurements, we hypothesize that the brain is inferring the cause of the measurements using the Bayes rule. So with this simple model, what you want to do to design the stimuli that are useful to understand how the brain works is to understand the knowledge about the measurement performed by the brain. And then you can build a generative model of your stimuli, right? And so then if you're able to generate stimuli with this model, well, you can better understand what is happening here. And you can compare the posterior to the posterior that you use to generate the stimuli. So I will start talking about dynamic Gaussian texture synthesis. So yeah, I provided the theoretical work with 3 equivalent formulation. I won't go into these details, but it allows for on-the-fly synthesis, and we applied this model to understand better motion perception. And so all these stimuli are mostly designed to study the primary visual cortex for neurophysiologists. And so then I will move to more naturalistic texture synthesis. So algorithms that are able to capture a broader range of textures. So I will briefly introduce the method and how it differs from previous methods. And we will study how we perceive interpolation between texture when we move continuously from one texture to another. I won't talk about neural recording. And here, this is more adapted to study the mid-level visual cortex, because this is where they should be. I mean, this texture have more content, and somehow they activate more the mid-level visual cortex. So let's start with the dynamic Gaussian texture. So in the field, as I said, the stimuli are either deterministic or stochastic, but there is no specific parameters. So you were defining a law on the position of pixel value or on the law of small gabors. And when it's stochastic, like every experimentalist is using his own implementation, and there is no like there's so many different libraries that are available to craft stimuli like this. So yeah, there's a lack of uniformization in the field, and also most of the stimuli were static, and there's a lack of a dynamic aspect in those stochastic stimuli. And last, it's often the contrast of the stimuli that is used as a proxy for uncertainty, while we can control specific uncertainty for specific features in different ways. So a solution was given by Motion Cloud in 2012, and this is based on this work that I expanded a bit the definition of the stimuli. So there is 3 ways of seeing these stimuli. So different tools to further models your data. And one important aspect is that it's a solution of a partial differential equation, which means we can synthesize the texture on the fly, frame by frame. And so here there is some ways to make progress towards non-stationary synthesis, which could be interesting. And so I will mostly talk about the demonstration and empirical data here with a study of motion perception. So I can show you those stimuli. So basically it's Gaussian texture. So it means they are all parameterized by the power spectrum. And so in fact, you can define the density of the spatial frequency content and the temporal frequency content of this stimuli. You see 2 examples here. And as I said, it's a solution of a partial differential equation. So when you discretize and you do finite difference, you can compute the next frame as a function of the previous frame. And you have the parameters that you can control here. And so this tool is available at the ECN, so the formerly UNIC where I was working. So they continue to use it now. Yeah, I wanted to show an example, dynamic example. It looked like. And so you can modify different parameters here. So with these natural movies, I derived the closed form expression of the power spectrum. And so before that, people were studying natural movies and trying to guess what is the distribution of speed in natural movies. Well, when you do the spatial analysis, of course, you find again this power law in the decrease of the power spectrum, which is related to the scale invariance of images. And as a proxy for the speed distribution, they were looking at these variables, so the power spectrum multiplied by frequency, as a function of omega over f, which is homogeneous to the speed. And so for them, this was the distribution of speed. So with my axiomatic approach, I was able to relate the speed distribution to the power spectrum. And so this is what you get for the power spectrum. And you see you have the distribution over the spatial frequency modulus, and here the spatial frequency orientation. And so this define mostly like the characteristic frequency of the stimuli and its orientation. And for the speed, there is a little transformation, in fact, of the speed distribution. And as you see, this is true that it depends on omega over f here, like here. And so what is interesting here is that, in fact, if you change with this approach in the power spectrum, as f, the modulus of f is in the denominator, it will affect the variability of speed perception. So depending on the spatial frequency, you will be more confident or less confident. I shouldn't use confidence, but you will be more certain or less certain about the real speed that is shown to you, which means the standard deviation of speed is decreasing as the spatial frequency is increasing. So the question was, what is the effect of spatial frequency over speed perception? And so we use two alternate first choice experiments where we present consecutively two stimuli, and we ask which one was faster. So here's a small example of the trials. This is one. This is another one. Right. I can play it again. Normally you have the impression that the second one is slower, while in fact they have the same speed. And the only variable that is changing is the spatial frequency, the average spatial frequency of the stimuli. And so in these two alternate first choice experiments, in one stimuli, the reference speed was always present, while in the second stimuli, the spatial frequency was always present. Well, we randomly interpolate everything, of course. And so you always compare these two stimuli on two different axes like this. So yeah, this was the trial example. And so after the presentation of the two stimuli, the question is which is faster, and you answer yes, no. And the model behind that is that we make an internal measurement M, and we estimate the speed for each stimuli, and then we compare the two speed. So we have a speed distribution, the estimate knowing the true speed on the screen, and from that we can derive the psychometric function. So these are the two distributions for the stimuli, and you compare when this random variable v and v star is higher. And so this leads to this psychometric function here. So I will recall everything about the psychometric function here. So usually psychometric function you will compare. So for example, with if all the other parameters, so the spatial frequency is the same, you compare stimuli lower to v star, and so you will likely answer that it is slower. And so if you present a higher speed, you will likely respond that it's faster. So you have a psychometric function that goes from 0 to 1 like this. And at 0.5, which means when you present the two stimuli that have the same speed, normally you answer randomly. Half of the time it's one, and half of the time it's the other. And so this is called the point of subjective equality. So if you start changing, another parameter interesting is the slope at the base, which will represent the sensitivity to a change in speed. And so what we can observe if we change the spatial frequency is a bias, which means that the point of subjectivity is shifted toward higher speed, for example. And we can also observe a change in sensitivity, so a change in the slope. So usually what you measure in the psychometric function is this bias mu. So how it is shifted from v equal v star, and the slope, so this sigma z star. And so we can recover this function using a Bayesian approach. So we will suppose that the observer uses a maximum posteriori estimator. So you just maximize a combination of the sum of the log likelihood and the sum of the log prior here. And what it means is that when you combine a likelihood with a prior, which is the exponential decreasing function here, your posterior will be attracted by the prior. So when the prior is high, your likelihood is shifted towards slower speed here. And so when we combine and you compare two estimates like this, you can relate, so you can find this psychometric function where you have the parameters of psychometric function that depends on this variability of your estimate of the stimuli and the slope of the log prior here. And so what we did, in fact, is to relate mu, the bias, to these two parameters and the slope to these parameters. And in fact, it means that this bias is related to this sensitivity. So this is an old version, and this result has been set up, have been established more generally now. And so this is the result that we observe. So here I show so we tested the various set of conditions. I won't go into the details, but overall we observe a bias that was so not consistent among all participants, but on average, this is the behavior of the group of participants. There were only 5, so the experiment is very long to perform, and it's very tiring for a participant. So yeah, when you see speed, it's difficult to get psychometric data. And so we also, it's very hard to see because there is a lot of variability, but overall the sensitivity. So here this is the sensitivity is decreasing with higher spatial frequency. But those are the results with just a psychometric fit of mu and sigma. And you can do a fit of the Bayesian model, and you find that here you will recover the bias, and also this bias is in fact explained by a decrease in sensitivity. So here this enforce. So when you do a basic fit, you are not enforcing any decrease, but here this will force the decrease to also be consistent with the bias. So it's often hard. I mean, there is a lot of variability. So in fact, for me, the conclusion that you get there when you get there is you need more participants. But still, so this is somehow consistent with some participants. It's very consistent, and on average, it's good enough. And so when you check the parameters of the Bayesian model only, you see that yes, you find a prior slope that is negative, which means you have a prior for slow speed, which was previously found in other papers. And you find that yes, the latitude width, so the sensitivity is decreasing. So I will move now to naturalistic texture synthesis. So here I'm talking about the texture with like a more complex than just Gaussian textures. You are somehow limited to you cannot synthesize texture with some structure with the previous model, for example. So naturalistic texture synthesis were used a lot to study vision. So for visual categorization, crowding, search. It has also been used in a model for peripheral vision, and also to identify regions of the brain that are specific that are texture selective. And there is more paper about that. So mostly it was, so they use an algorithm that was done by Portilla and Simoncelli. And this is really a smart engineering design here, because they just compute a wavelet transform and they compute a lot of statistics on this wavelet transform. And when they adjust these statistics, they are able to synthesize a texture that is similar to an example texture where they measure all these statistics. And more recently, using deep networks, Gattisal got really like similar results in terms of texture synthesis. But you have less statistic to handle here. So they simplify a bit the framework. But they were not based on theory. And there is no like, really understanding of their effectiveness. So for me, this will limit the perceptual study and its modeling, and also the understanding of neural activity. So here I show that in fact, you can understand the statistic of texture in a deep net as being elliptical, which means mostly the distribution is unimodal and with elliptical symmetry, which means you are mostly parameterized like a Gaussian with a mean and covariance, but you are not necessarily only Gaussian. You can have heavy tails, but you're still unimodal. And I propose a mathematically grounded theory of texture interpolation using optimal transport. And using these textures, I will show how we can study the interpolation between textures and how the space are perceived. And to relate when you move from one texture to another, how do you perceive the change along the line? And finally, there is also a question that we can ask in neurophysiology: how the neural activity is changing along the path, but I won't go into the details here. So you see, so those are the example result of the algorithm. So either Gattis algorithm or Pottier symmetry algorithm, or MI, when run on texture and natural image. So you see that it's scrambling every object in the image, while it's fine to scramble the texture. And so the idea here, I propose a metric to measure ellipticity. So if you are elliptic, if you are Gaussian, you are really elliptic, right? So the distribution is very narrow. And here what you want to understand is the narrower the distribution, the more elliptical you are. And so for natural image, well, you have a lot of, you are broader than texture. And so this led me to conclude that texture activation are more elliptically distributed than natural images. And so when you have an elliptical distribution and you want to match distribution together, a natural tool is optimal transport, because it defines a metric of a probability distribution. And so for elliptical distribution, and specifically for the case of Gaussian, the distance between two Gaussian is so the squared distance here is the sum of the squared distance between the mean and the square formation between the matrix. So to understand that, you can understand it in one dimension. This would be the Euclidean distance between the 2 points in the mean standard deviation plane. So here it's only sigma, right? If it's in one dimension. And so what it means, for example, is that you can define a geometry of a probability distribution. And so you have a distance and also the existence of a shortest path. And these shortest paths are not straight line, or maybe they are straight line in a specific space, but we say that they are geodesics. And so here's an example of what is happening when you move a Gaussian towards another one, right? So it means you know perfectly how to move between one density to another one. And so if your texture are characterized by densities, then you can interpolate between textures. So this is what we are using to calculate a loss function to generate textures, given the statistics of an example texture. And we can also interpolate between texture. So if this is one texture and this is another texture, you will be able to move along the path. So how to synthesize the textures? So you compute all the deep net coefficient at several layers of a deep network. And for each layer, you will compute this distance between the density of the features here. And so here, as I shown here, in fact, this end up just computing the mean and the covariance of the feature vector at each layer. So one feature vector is a collection of response of all neurons at a layer, and you compute the average of all the response across the image. And you can also compute the covariance. And so all these terms here that you add together will form a loss function that you initiate. So you have your example texture V that you know, and you're able to compute the reference mean and covariance at each layer. And your variable is U. You start with a white noise, and you will perform a gradient descent. So you will minimize L as a function of U. So you will move U, the pixels, towards the direction which minimize this sum of function here, which means you want to have the same statistics in the deep network. And so this is how it works, and how you can then interpolate. Well, you just have to do a weighted sum of two loss functions like this. So if you have one texture and another texture, you do a weighted loss like this, and you minimize this function as a function of U. And you will end up interpolating along the path as t goes from 0 to 1. So here are some examples. So on both sides, you have the original texture, and inside you have like the interpolation between the two that was synthesized. Right. So you see that it's, I mean, it's along the path. So if you synthesize texture that are close by, well, they are similar. So for me, this is an appealing perceptual. It's consistent with perception. And also it generates stationary textures. Like every patch here is a stationary across space, which is also a property that we have on textures. Yeah, more examples. And I observed that not all interpolation paths are relevant for perceptual study. So I use the Portier-Simoncelli algorithm, where there is another way to perform texture interpolation, and this was used also in neuroscience, in electrophysiologic studies and perceptual studies. But this is not grounded in any theory, but it works, which is incredible. It generates patches that are similar to what I'm able to generate. But if I use the first texture synthesis algorithm that was crafted using deep network, here it doesn't work. And here, in fact, they were not using the mean and covariance. They were using the Graham matrix, which is related to, I mean, which depends on the mean and covariance, but it does not define a proper distance. And you see that when you go through the interpolation path, in fact, you are just putting patches of each texture at different places in the image. So it's not stationary. So if you were to study like how do you perceive the texture along this path, in fact, you would just study the perception of areas or something like that, and not the perception of a change, a subtle change in the statistics between this texture and this texture. So we did two things. So interpolating between the Gaussian version of the texture, so which would be a model like the first one I presented, which mostly target V1. And in this way, you would increase the naturalness. This is how they call this change in parameters in this paper. And you can also interpolate between arbitrary textures, which means you are changing higher order statistics here. And what is appealing is that all of it depends on on probability distribution in the layer of the network. And so you can ask the question how the paths are perceived, and also about how change the neural activity along the path. Yet I will focus on how the path is perceived here. So to understand that, we used what we called maximum likelihood difference scaling approach, in fact, which is able to measure a perceptual scale. So this method was used for color perception. So usually it's useful when you don't have a clear understanding of a question to ask. So if I were to do a 2FC experiment on texture, I don't know how to ask a question, right? I would always have to show the reference texture to understand something. While when we ask which stimuli is faster, it's clear what is faster for everyone. So here we can do 2FC. But so here for interpolation, we want to compute the perceptual scale. And so the idea is that there exists a melodic function from 0,1 to 0,1 that maps the interpolation path to perception. And so in fact, this is a function that relates the external world to the internal world. And so here you have a representation. It means that, for example, here a small change in the physical world causes a large change in the perceptual world. And on the opposite here, a large change in the physical world only cause a small change in the perceptual world. So you are not sensitive here and you are highly sensitive here. And the way you compute this function is through comparing. So this is the assumption of equal comparative judgments, which means that when you compare two stimuli, so in your perceptual space, you will compare the difference of the difference between two stimuli. And these differences are assumed to be corrupted by a noise with constant variance. So we'll see what it means in other terms later. So the protocol to do that. So here the physical parameter is the interpolation weight between two textures. So we sample them equally between 0 and 1. And you will present 3 different stimuli ordered like this. And so the task is to say which of the 2 bottom stimuli are more similar to the top stimuli. So here you will answer this is the right stimuli. And so with this triplet, you are estimating a probability PAGK that one of the 2 bottom stimuli is closer to the top stimuli. And so, as I said, you in fact, with this probability PAGK, in the model, it's from the computation of the difference. So you compute the difference between these 2 and the difference between these 2, and you compare the 2 differences. And then you want to know whether delta IJK is higher or lower than 0. And so the expectation of this random variable here, the expectation of this random variable being above 0, is in fact just can be expressed as this function. So here, this is a cumulative distribution function of normal, which is a function of the 3 value of the function phi here. In fact, you can remove the absolute value because you can also always assume that everything is ordered. And so this expectation is approximating this probability PAGK. And so ultimately, you can just invert this function, and you just need to solve a linear constraint system to recover the function f, so which is phi here, majuscule F, capital F, sorry. So we measure that on texture by interpolating, so between the Gaussian version of the texture and the more natural texture on 8 participants. So here for 3 texture, here we observe like similar trends and are barely different from the identity, but consistent. So if we were to answer randomly to the experiment, you will have a huge variability in gray, and you will find the identity. So here we find something close to the identity, but with small error bar, which means that the behavior was consistent across participants. We also interpolate between arbitrary textures, and here we find more variable results and also consistent, more than noise. And there's an extra variable, this constant internal noise that is assumed, that is of course estimated to be lower from the true interpolation and for a random answer and presentation of noise. So it means that when you move here to a texture, you perceive the change. So here the change is slow, and here you are more sensitive. So you move a small amount toward this texture. At this point, you will be more sensitive. And so what is interesting here, in fact, using the information theory, and so a lot of stuff that I didn't present because I don't want to go into these details. You're in fact able to predict what would be this function from the statistics of these textures. And so this is what I did. And so I have statistics at each layer. So I did that for each layer of the convolution network. And I did that also for wavelet coefficient and for pixels. So you see that when you use only the statistics of pixels, there is nothing visible. And when you look at the statistics of wavelet coefficient, you start to have something that is somehow consistent with what you observe. So the colors are the same. I was really happy to see that the purple one is above, like we observed here, and the two other are below the identity. And this is consistent across the curve layer, and on average, this is consistent. So I found that, but it's somehow too innovative here. And when I talk to people that are studying visual perception, they would say, no, but you cannot validate your theory with textual interpolation and all that. You need to go back to more classical aspect. And so I stopped here just with this observation. I will show now how we can go further. So in terms of this type of experiment in relation to information theory, but also in terms of pushing further the model of Gaussian texture that I showed. So I will talk, as I say, about dynamic Gaussian texture again, and also information theory, perception, and experiment. So the idea is that I want to test this information theory prediction in a more classical setting, so mostly using orientation, for example. And also this theory will provide relation. I mean, it's able to account for what you observe in a two alternate forced choice experiment. So the measure of the psychometric curve that I talked at the beginning of the talk, and this maximum likelihood difference scaling function. This could also be used to study suboptimalities in perception. So here I will show you what it means and what is behind that. So you're still using this function. So you have a physical parameter that is transformed towards your internal space, and this is corrupted by a noise with constant variance. So this is the main equation here. And so, in fact, this equation is able to recover the model that we use to calculate this MLDS function. And here, this is what you would measure in the 2FC experiment. So you measure the psychometric curve, and in the psychometric curve, there is bias, but there is also the slope that is changing. And so, in fact, this model together predict that this is a function that is transferring this set of psychometric function across the physical space into a set of psychometric function that is homogeneous, meaning that the point of subjective equality and the slope are both constant. And so this is somehow like understanding that this transformation is optimal in terms of information theory. And so what I want to test, so I'm currently working on that, is so I will show you the relation that I want to test. So if we assume that the bias and threshold both depends on the reference stimuli, it means that there is a sigma S that is not the same across the physical space. And so the stimulus is corrupted by stimulus noise. And so if you take the function f or that, and you do, you say the small is small, you can do a Taylor, first order Taylor development here, and you find that so the function of the stimuli plus noise is equal to the function of the stimuli plus a noise. And so you can approach that to this noise with constant variance. And so you end up saying, okay, this noise here is the same as this one. And this means that in the Gaussian hypothesis, but this is not necessarily needed, but here you end up with this relation, which means that the sigma that you, so the noise that you have in this approach, the MLDS approach, is the same as the product of the stimulus noise times the derivative of this function. And so I'm currently doing experiment to measure psychometric function here and MLDS function, and to see how close we are from verifying this identity. And then maybe we will be able to move towards things with more complex textures and to validate this theory further. And so finally, I want to come back on the dynamic texture synthesis algorithm. And so I think we can go further. So for example, if you do psychometric experiments, or you can add like some recording device, measuring EEG or MEEG, for example. And from this signal, maybe you can modulate the stimulus again and update the stimuli online. And so maybe there are really interesting questions behind that. One is, for example, are you able to modulate your EEG signal by yourself to provoke a change in the stimuli, and are you able to learn to do that? Right. So that's really interesting future avenue for me. Thank you for your attention.